Okay, let's talk about alternating series and absolute convergence. So, an alternating series, first of all, it's a series that basically looks like this. The word alternating is referring to the sign, as in negative or positive. And so we're going to consider a series that has this -1 to the n minus 1. The fact that this is n minus 1 is hardly important. This could be n or n plus 1. The point is, this part makes it have a positive, negative pattern. In other words, an alternating sign pattern. But just for the sake of nailing things down, let's say that this is -1 to the n minus 1 times b sub n. And so this series, the first term is b sub 1, and then negative b sub 2, and then positive b sub 3, and the next one would be negative b4, and so on. So here's the alternating series test that can tell you when such a thing converges. If we have, first of all, these numbers b sub n should be positive, and b sub n is like the part without the -1 power. So basically there can't be any funny business going on with having a negative here, and then this is b sub n is also negative, and then it cancels out to be positive. We don't have that going on. The numbers b sub n themselves are positive. The only thing contributing to whether we have a positive term or a negative term is this. Like, this is what makes it negative. It's not that b sub n is a negative number. Anyway. So if we have that, and if we have that the sequence is non-increasing, meaning that the next term is always less than or equal to the one before it, so b sub n plus 1 is less than or equal to b sub n, and, of course, we require that the numbers b sub n go to 0 as n goes to infinity in order for this series to converge. So if all three of these things are true, then the original series converges. So this is a fairly easy test to use as long as you remember to check these three things. Okay. So we are now going to also introduce the concept of absolute convergence. So we say that a series, and I didn't write anything on the bottom or the top, n starts at somewhere and it goes to infinity. But I don't want to be too particular about where n starts. N could start at 0 or 1 or 2 or whatever. But this is an infinite series. We say that this series is absolutely convergent if the series that I get by taking the absolute values converges. So in this situation, some of these numbers a sub n might be negative, or they might all be negative, or maybe some positive, some negative. And we take this other series by just making all the terms positive. And if that new series converges, we say the original one is absolutely convergent. And why do we say that? The phrase absolutely convergent would kind of make one think that that means that the original series is convergent. We're calling it absolutely convergent, so one would think that it's convergent. And that's what the next theorem says, that if a series is absolutely convergent, then it's also just regular convergent, like without the word absolutely in there. In other words, if this series, the one with the absolute values, converges, then the one without absolute values also converges. So this brings us to basically there's another type of question that I can ask you now based on the following definition. We say a series is convergent. Well, sorry, let me start that sentence over. If we have a series that happens to be convergent, but it's not absolutely convergent, then we call the series conditionally convergent. So that means that the original series converges, but it's not absolutely convergent, meaning that the series with absolute values there diverges. then we call this original series conditionally convergent. So there's a new type, like I was saying, there's a new type of question I can ask you, which is whether a series is convergent or absolutely convergent, conditionally convergent, or divergent. There's three choices. Anyway, let's do an example. So let's just use the alternating series test to tell whether a series converges or diverges. So here we have an alternating series. It's not quite like the one in the theorem that I stated because it doesn't have -1 to the n minus 1. It has -1 to the n, but let's not be thrown off by that. This is still an alternating series. So let's check our three things. Actually, maybe I still want this here. Let's check our three things. So for us, B sub n is basically the non-alternating part. I'm just going to ignore the -1 power, and so B sub n is 1 over n. Well, let's check our things. It's positive for all n, and when I say for all n, I just mean like the relevant values of n. N starts at 1. So as long as n is at least 1, 1 over n is positive, sure. Next thing, B sub n plus 1 should be less than or equal to B sub n. 1 over n plus 1 less than or equal to 1 over n. That's also true, and we're just going to use the simple logic that we've used a few times, that both sides are fractions, they have the same top, and the bottom of this one is bigger than the bottom of that one, so that makes this fraction smaller than that fraction. So we're good. Let's check the last thing. The limit as n goes to infinity of my B sub n should be 0. Sure enough, it is. As n goes to infinity, we've got 0 there. So we got 3 check marks, so the conclusion is that the series converges. And just in case there's any doubt, we are talking about the original series. It converges. Notice in this question, we were not asked whether this series is absolutely convergent or conditionally convergent. It turns out that this series is conditionally convergent, but we weren't asked that. So I'm about to do another example where we are asked that question about a different series, but for this one, we just wanted to say whether it converges or not, so we're good. All right, so here it comes. Here's the other example. I'm going to take this series and ask the question that now has 3 choices. Is it absolutely convergent, is it conditionally convergent, or is it divergent? So, yeah, there's a couple of ways. I mean, what we do first is kind of up to us, so maybe I'll just pick something. So maybe first, let's consider the series where I put absolute values around this. Right, this is like, where did yeah, here we go. It's like I'm starting with a series and I'm just going to write the series where I put absolute values around a sub n. So I'm just going to put absolute values around. Okay, so I'm going slow because this is the first time we're doing this, but all the absolute values do is they remove this -1 power. This number for all n at least 1, this is a positive number. The only thing that could possibly make it negative is this, so if I just drop that, that's what the absolute value is. We could have just gotten to here in 1 step if we thought about it, but like I said, this is our first time, so I'm going slow. Okay, so the question is whether this series converges or diverges. So here's what we're going to do. This looks like I want to use the limit comparison test. For the limit comparison test, we have 2 sequences, a sub n, which is, I always just make it the original, and then there's b sub n, which I call sort of an approximate simplified version, or what I do to come up with b sub n is I look at a sub n and I only keep the important parts. So the important part on top is an n, and the important part on the bottom is an n squared. So for polynomials, it's just the leading term. In other words, b sub n is just 1 over n. So to apply the limit comparison test, I am supposed to do the limit as n goes to infinity of a sub n over b sub n. And get a positive finite answer. So let's see if I do. I should, because I came up with my b sub n using the standard method, which really should always work, but let's show our work here. So I'm flipping the bottom of the fraction. I've got n squared over n squared plus 4, and at this point I am comfortable enough just using the shortcut where if you're doing the limit as n goes to infinity and you have a polynomial over another polynomial, it's just the ratio of the leading terms. So leading term here is n squared, leading term here is also n squared. I'm going to get 1. You can show more work if you like using L'Hopital's rule, but I'm using a shortcut. So what are we looking for? Well, this was supposed to be positive and finite, which it is. Great. So what does that tell us? According to the limit comparison test, the series that we make by putting a sigma in front of this and the series that I get by putting a sigma in front of this, they do the same thing. Either that both series converge or they both diverge. So what I'm going to do is I'm going to investigate b sub n now. So the series that I get by putting a sigma in front of my b sub n, look, that's a p series. P is equal to 1, and a p series diverges if p is less than or equal to 1. Therefore, because we knew that these two series do the same thing, this one also diverges. Okay, but we are not done with this question yet. Let's take a step back and examine where we are. The original series was this. It had this -1 to the n minus 1. We just investigated the series that we get by putting absolute values around it. And just to remind everybody, we're wondering whether this original series with the -1 there, this is an alternating series, we're wondering whether it's absolutely convergent, conditionally convergent, or divergent. What we've concluded so far is that when I put the absolute values around it, it doesn't converge. So all we know now Let me put this in a little bubble. I don't know which one of these three things the original series does, but I do know that it's not absolutely convergent. Because absolutely convergent means that if I put the absolute values around it, then that new series would converge, and that's not what happened. So that's where we are now. We still just have to decide whether it's conditionally convergent or divergent. To answer that question, we have to go back to the original series that has the -1 to the n-1 on it. So let's go. So I'm going to keep this. So now this is what we're investigating. This is an alternating series, and we can just use the alternating series test. We have, okay, so for the alternating series test, we let this b sub n, or maybe, because I already called something b sub n in this problem, maybe I'll call it c sub n or something. That's what we'll say. So b sub n, or in this case I'm calling it c sub n, it's basically the absolute value. It's the version where you don't have this -1 there. So c sub n is just n over n squared plus 4. And we have to check a few, we have to check a few things. It is supposed to be positive, and again, n is at least 1, so the top is a positive number and the bottom's a positive number. So that's fine. Let's talk about the next one. Let me just write down what it would say. So here is my c sub n plus 1. I just took my c sub n and I replaced all the n's with n plus 1's. And I'm hoping that that's less than or equal to c sub n. It's not entirely clear that it is. And we should really be checking these things. We should not just be blindly putting check marks. It's not so clear because I can't use my simple reasoning that, so sometimes we have two fractions and I just compare the tops and I compare the bottoms. But when I look at these two fractions, the top of this one is bigger, like on the left, the top is bigger and the bottom is also bigger. And it's unclear what effect that has on the fraction. If I make both the top bigger and the bottom bigger, then, well, it depends how much bigger I'm making the top and how much bigger I'm making the bottom. It's unclear whether the resulting fraction ends up being less than or equal to the original or not. So we're going to have to do something here. Here's something we can resort to. If I let f of x be this function, but of course with x's instead of n's, I can check that this is a decreasing function. Decreasing meaning if I plug in a larger value of x, the function becomes smaller. If it's decreasing, then I'm going to put a check mark for this second star. And I can check whether it's decreasing by taking the derivative. So f prime of x is, okay, bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So we're like that. So what do we got here? This is going to have an x squared, and then I'm subtracting 2x squared. So let me write negative x squared plus 4. Okay. And I'm hoping that this is decreasing, of course. I want to put a check mark here, but I'm not just going to do it without actually checking. So I'm hoping that this is decreasing. I'll be able to tell that it's decreasing if the derivative is negative. So let me take a look at the derivative. I have a sort of a complicated looking fraction here, but once I start picking it apart, it's not that bad. The bottom's definitely a positive number because I see something squared. So whether the entire fraction is positive or negative just depends on the top. And the top is just 4 minus x squared. So if x is at least 2, then this is going to be less than or equal to 0. Or in fact, let me say this is less than 0 for x greater than 2. So what does that mean? So this function is decreasing when the input is greater than 2. So let's say, of course, n has to be an integer, and n is like taking the place of x here. So if x needs to be greater than 2, let me write n greater than or equal to 3. So a quick remark, we are using the alternating series test, and these 3 stars, these things that we check, technically it says for all n. But remember, the first few terms of a series have no effect on whether the series converges or diverges. All of these, as long as these first 2 things are true for all n large enough, it doesn't really need to be true for all n. If it's true for all n that's at least 10 or at least 100 or even at least 1,000,000, or in our case at least 3, that is good enough. In fact, let me put a little remark here. We can still use the alternating series test if these first 2 things are true for all large n. Of course, the third thing is kind of obvious, that there's nothing for me to say regarding this remark for the third thing, because the third thing is literally the limit as n goes to infinity. So the third thing is already for all large n. Okay. In conclusion, I'm going to stick a check mark right there. Because we got it for all n large enough, we've got it. Okay, I swear we are almost done. There's the third star where I just check that the limit as n goes to infinity of my b sub n, or in this case I'm calling it c sub n, is 0. And for this, we can just use the shortcut again, because the top and bottom are polynomials. I like to phrase this shortcut as just saying that when I'm doing the limit as n goes to infinity, the only thing that matters on the top is the leading term, and the only thing that matters on the bottom is the leading term. So this is going to give me the same answer. Of course, this is the same as 1 over n, and 1 over n goes to 0. And that's what it should be, or that's what it needs to be if we're using the alternating series test. Okay. So the series, oops, there's an E in the word series. And to be absolutely clear, I am referring to this series converges. So this is why you see me all the time sort of drawing arrows to make sure that you know what series I'm referring to if I'm going to say the series converges. Because if you think about the problem that we're doing, there's really multiple, there's the original series, there's the first one that we considered, the one that has absolute values, and that one diverged, and then we said, okay, now we need to consider the original series again, and that one converged. So I need to be careful, to be clear what I mean when I say the series converges. I need to say which one I'm talking about. Anyway, we have our answer. So what is our answer? It turned out that the original series, which is the one that we just investigated, that one converged. And if you remember forever ago, when we investigated the series that has absolute values there, that one diverged. So this is what we call a conditionally convergent series.